This lesson's on drawing Lewis structures. The purpose of Lewis structures is really to illustrate the bonding of the valence electrons in both ionic and molecular compounds. Lewis structures look like this, with little dots that represent the number of electrons that a particular atom has, and the exchange of those electrons between atoms to form these chemical bonds. And so the one key thing to recognize is that any bond that's connecting any two atoms must require two electrons. Our first task today is to be able to look and quickly count the number of valence electrons that are in an atom using the periodic table. So quick review, remember that valence electrons are simply the highest energy level electrons in an atom. Going back to the last unit, one of the things that we did was write electron configurations. And so as a quick reminder, here's sodium. It has 11 electrons, and so its electron configuration would look like this: 1s2, 2s2, 2p6, and 3s1. What we'd like you to be able to do is to use your electron configurations to quickly count valence electrons. So if I look here, remember valence electrons are the highest energy level electrons, and so the big numbers that correspond in front represent the energy level of that those electrons are in. So first energy level, second energy level, and third. So sodium has its highest energy level is 3, and as you can see, there is 1 valence electron in that atom. Chlorine, on the other hand, has 17 electrons. So here's its electron configuration. My highest energy level here is energy level 3, and in the third energy level I have both an S sublevel and a P sublevel. With 2 electrons in the 3s and 5 electrons in the 3p, chlorine has 7 valence electrons. And here are 3 other examples. What we'd like you to quickly be able to do is to recognize that only S's and P's in the highest energy level correspond to valence electrons. If I come down here to nickel with its 28 electrons, this would be its electron configuration. It has electrons in the first, second, third, fourth, and here again back in the third energy level, because remember the D sublevel gets filled after the 4s. So nickel, the highest energy level, is the fourth energy level, and you can see it has 2 electrons in that 4s and therefore has 2 valence electrons. And traditionally, this 3d electrons are not classified as valence electrons. So real quickly, what we want you to recognize is that S's and P's are the only thing that correspond to valence electrons. So if I go back to my periodic table and we look at the different groups that we have, here's my S group, my D group, my F group, and my P group, only the S's and P's correspond to those that are valence electrons. So you can quickly count the number of valence electrons by simply getting in the row they're in. Sodium, as an example that you saw a bit ago, has electrons in the first, second, and third energy level. And again, it only has 1 electron sitting right here that is in that energy level. So sodium would have 1 valence electron. Carbon, on the other hand, which sits right here, I get in the row it's in, and I simply count S's and P's. So 1, 2, 3, and 4. Carbon would have 4 valence electrons. If I get down here inside the where there are is in the D block, and if I wanted to take something like iodine that sits right here, what I would do is get in the row that it's in, but count only the S's and P's because the D's are behind. So to count iodines, I'd go 1, 2, skip all the F's, 3, 4, 5, 6, and 7. And that would end up with my 7 valence electrons. So again, if you run into this D block or this F block, they're always behind, so you just skip those and count those. And so that's how we can count the number of valence electrons for any atom, just quickly looking at the periodic table, is by getting in the row they're in and simply counting their S's and P's.